Thank you so much. So this is the first chapter in Unit 3. It's kind of a short chapter, but it takes kind of a while to really catch on to some of the concepts. So anyway, we'll just get right into it. So here's a molecular formula. What the molecular formula does is it tells us that there's 2 carbons, 6 hydrogens, and there's 1 oxygen. But it doesn't tell us how those atoms are bonded to each other. You could take that same formula and it could represent ethanol, which is this partial structural formula, or ether, which is this partial structural formula. So this is not enough information. We need 3-dimensional information. So I broke this up into 3 major sections. One is simply getting the structure, and then getting the shape, and then predicting the properties. So I'm going to run you through the whole thing here using water as an example. So we'll go through all A, B, and C, and D. And for water, it's just a preview. And then we'll come back and do some more detail. So here's water. That is the molecular formula. What we need to do to figure out what's called the Lewis electron dot theory, to get the Lewis structure, is we have to decide which one is going to be the central atom. So hydrogen tends to form only 1 bond. Why is that? Well, because of its position on the periodic table, you could predict that. So here's hydrogen. What does it want to do? Gain 1 more electron to be like helium. Now it's 1s2, which is electronically stable. So we think that hydrogen is going to form only 1 bond. Oxygen, on the other hand, is a nonmetal. It's right here. It wants to gain 2 more electrons to become like a noble gas. So it wants to form 2 bonds. So I would predict that oxygen will be the central atom for 2 reasons. 1 is the least abundant, and 2 is the one that forms the most number of bonds. So when I put oxygen in the middle, I put 2 hydrogens around it in kind of a symmetrical way. And then I have to put in all my Lewis electron dots. So I have 6 from oxygen, 1 each from hydrogen. So that gives me a total of 8. And where am I going to put them first? Well, I drew this line here representing a covalent bond because hydrogen and oxygen are both nonmetals. I have to put electrons in there. So where do I put my 8 electrons? 2 in that bond, 2 in that bond. So that takes care of 4 of them. Where do I put the other ones? Well, hydrogen is already happy. It's got 2 electrons around it. Just pretend like it's 1s2. So I'll put the other 4 on the oxygen. So now the oxygen has 2, 4, 6, 8 electrons around it, which represents S2P6, which is the noble gas electron configuration. So now, as far as we're concerned, we made every single atom in this structure electronically happy. So we would predict that that could possibly exist. So then where can we go with this? Well, one of the reasons why I said we put the hydrogens on opposite sides is because we know that electron clouds repel one another. So right now, looking at the central atom, I got 1, 2, 3, 4 pairs of electrons. And what do? They repel each other. So This is going to be a little bit hard to do with models and you're not having models to play with. But here, here's a model where I have 4, what we're going to call regions of electron density, and they all repel one another. So in this particular shape, which is called a tetrahedral because there's 4 sides, like 1, 2, 3, 4 sides. With this particular shape, this is how I get all those electron clouds as far apart from one another as possible. But now, 2 of these have hydrogen atoms on it, and 2 of them don't. It really doesn't matter which ones I put the hydrogen atoms on, but now I have a structure that represents water in a 3-dimensional way. So, a couple bits of terminology here. These are called bonding electrons. These are called non-bonding electrons, but they all occupy space around the central atom. So now if I'm looking at this molecule, what is the shape of this molecule? Well, to determine shape, we use a machine called X-ray diffraction. That means you take a solid form of the substance and you get it in an orderly manner. That's what crystals do. And then you shine X-rays through it and you look at what bounces the X-rays off. What bounces the X-rays are going to be the nuclei, right? Not these non-binding electron pairs. So what the X-ray diffraction machine sees is really this. So based upon that, we say that the water molecule is bent. But now what you know about repulsion of electrons, if I only saw this makes no sense whatsoever. Why would these electron clouds be close to each other when they actually repel each other? Well, the reason why they're in this bent configuration is because of these non-bonding electron pairs. So those non-binding electron pairs bend the hydrogen atoms down at that angle, causing it to be bent. So electron pair repulsion theory tells us that the water molecule is bent. So now we're going to go through predicting the properties. So we're going to use electronegativity. So electronegativity predicts the polarity of the bonds. So now if I'm looking at the numbers on the periodic table, oxygen is 3.44, hydrogen is 2.20. So the difference in electronegativity is 1.24. So that puts those bonds in a category of being known as polar covalent bonds. That creates a dipole. So what is a dipole? Well, a battery has a dipole, right? So you have the positive pole, you have the negative pole. But what is the net charge on a battery? 0. But with a battery, the net charge is 0, but you have an unequal distribution of charge, which you can then take advantage of to do work, right? This is potential energy. But this bond right here is also in that category of being a dipole because you have a partial positive charge here because the electrons are being pulled towards the oxygen. That make sense? This number, yeah, go ahead.
I had a quick question. Why do electron clouds repel from one another? Is it because they're of the same charge?
Exactly.
Okay, thank you.
So anyway, we have an unequal distribution of charge here because the oxygen is so electronegative, it starts pulling this electron cloud towards it and away from the hydrogen, leaving a partial positive charge on the hydrogen. That's the lowercase Greek letter delta We use that to indicate a partial charge, not a full charge. Then when I go to put the partial negative charge on the oxygen, what if I would to put it right there on the oxygen? Then it would look like there's a negative charge right where the nucleus is. So that doesn't make sense. So what we do is we move it out to the non-binding electron pair. So this represents the dipole between the hydrogen and the oxygen. And you know what? We have another one over here. So the point of the matter is, the water molecule now has partial charges. This has magnetic properties. And when you see that you have partial charges and it doesn't cancel out, in other words, if the dipoles don't cancel out because they're at this angle to each other, you have what's called a polar molecule. So the polar bonds have made it into a polar molecule. And that's going to lead us to be able to understand all kinds of properties about water and other molecules that are also polar. So what it really means is that water molecules behave like little magnets. They align themselves up in magnetic fields, and they're attracted to each other. So here's a slightly different depiction. I was able to find something to steal from a book over here, but most of the time I can't find anything that's really worth stealing on the internet because their information is partial or it's not clear. So now, knowing that water molecules behave like little magnets, this explains a lot of the behavior of water. First of all, water is a liquid. It's a very small molecule, but why is it a liquid and not a gas? There's a whole bunch of gases that are going in and out of your nose right now that are much heavier by factors of 2 and 3 than a water molecule. Why are they gases where water is a liquid? It's because little magnets are attracted to other little magnets. So imagine you going to the water faucet and you turn the faucet and you're trying to make one water molecule come out of that faucet at a time. Can you do that? No. They come out in big clumps of billions of water molecules all stuck together because each individual water molecule is a magnet.
Is that why you could say water is cohesive or adhesive? Is because how magnetic and clumped together they are?
Yeah, that's true.
Okay.
Another thing that we can explain is that why does water dissolve polar substances? Like ammonia, for example. Well, it's because little magnets are attracted to little magnets. So here's an ammonia molecule here. And I do need to redo this picture, but I have all this time on my hands. So for the ammonia molecule, here's the partial negative charge on the electron clouds. It's going to be attracted to the partial positive charge on the hydrogen atom of the water molecule. It's being attracted to this side or to each individual hydrogen. And why does ice float on water? This is really hard to do without having more space. But here's 2 water molecules, okay? This is how they would align. So this is the partial positive charge of the hydrogen. This is the partial negative charge on the oxygen. They would be attracted to each other like this. But this would be the case if they were at low kinetic energy. In other words, at low temperature. And what happens at higher temperature? Well, they're moving around faster and maybe enough to break those bonds, those attractive forces. But look what happens when you put them straight across from each other like this. You have all this volume in here. But if they're bouncing all around, they can be right up in each other's space because they're just moving so quickly. So look what happens. If I take this water molecule where the partial negative is being attracted to the partial positive, here it's aligning itself straight across. Same over here, and same over here in a three-dimensional manner. What that does is it leaves a void within the volume, a void between the water molecules. That void doesn't exist there under higher kinetic energy. So imagine, say this is ice. This is what you get in ice, right? 4 alignments like this in ice. That's at low kinetic energy. So what happens when you melt the ice? Well, you increase in the temperature, so the velocity of these particles increase. So this thing starts to bounce around much more violently. And eventually it's bouncing so hard because the temperature goes up that it's able to break this attractive force. And it can simply be in here or go over here or go over here. And when you do that, the structure collapses and the volume decreases. So why does ice float on water? Look at the density equation. The mass stays the same, but what happens when the volume goes up? Well, then the density goes down. That's the reason why ice floats on water. Oftentimes, if you take liquid water, put it in a glass, and put it into the freezer, it will break the glass. Why? Because the volume increases. And so we can explain a lot of other things as we go along in this course. I actually wrote a whole chapter on these types of attractive forces. I called them intermolecular attractions because it's extremely important for you to understand how the world around you works. So, in a very, very basic sense, here's a table. The table is very hard and it's a solid. What that means is that the attractive forces, whatever they are, that hold it together must be strong. What about the gases over here? They just freely move around. They're in the gaseous state. They're not attracted to each other. So the attractive forces must be extremely weak. If you look at a liquid, such as water, somewhere in between, well, the attractive forces are important. So this is the way we can actually look at the world. It's about attractive forces between particles. So what I tried to do is just give you an overall viewpoint of where we're going. Ultimately, we'll be able to take a molecule's molecular formula, get a structural formula, figure out what its shape will be, figure out what the bonds will be, whether they're polar or non-polar, or ionic even, and then we will be able to predict certain things about its chemical properties, physical properties. It's a very powerful way of looking at things. So what we're going to do is just go right back to the beginning and we'll start with getting the structure. Lewis electron dot theory, this is the same Lewis that came up with the Lewis structures for atoms and ions that we had in the previous chapter. So the first 3 steps are going to predict the bonding, and the last 3 steps will prove that that bonding arrangement is possible. So we first have to identify what is the central atom. It will be the least abundant atom and the one that can form the most number of bonds. Now, in general, this is a pretty good guide. Hydrogen, chlorine, fluorine, all those things, they want to do one thing to become like a noble gas. So they're going to form only one bond. Group 2 They want to gain 2 electrons to become like a noble gas, so they form 2 bonds. Same thing with group 5 and the group 4. Okay. So this is just a general guide. Then what do? We arrange the other atoms around the central atom in a symmetrical way. And why do I keep using the word symmetry? It's because electron clouds repel each other. So if I take off all the atoms, all the outer atoms of this, this is the way to get all these electron clouds as far apart from one another as possible. Here would be another way with a different shape. That gets those 3 electron pairs as far apart from one another as possible. If you did something like this, would that make sense to you?
No.
Hopefully not. My finger and hand workout using those models. So then what do is we simply connect nonmetals with lines representing covalent bonds. And we will not draw covalent bonds between a metal and a nonmetal, regardless. For no reason will we do that. This is simply a convention that we'll adopt. It just makes everything more simple. So then the last 3 steps prove that the bonding arrangement is possible. So you add up the total number of valence electrons using the group numbers from the periodic table, and you distribute the valence electrons as pairs, first into bonds, then into outer atoms, and then finally to the central atoms. So the outer atoms should get an octet, which just means 8 electrons around it, which signifies S2P6. Hydrogen gets a duet, in other words 2, representing 1s2. Okay. So look at the strategy here. And I know you're not supposed to anthropomorphize when you're a scientist. I do it anyway because it works. Why do we put the valence electrons first into the bonds? Why do we do that? Because you drew the line to show that they're connected there. Now you got to put the valence electrons in there. Why do we do it as pairs? Because stability is full orbitals, right? So first we put them into the bonds, and then we put them onto the outer atoms, then finally to the central atom. What that means is this. The central atom is choosing to be the central atom. That means if there's ever a case where there's not enough electrons to go around, or there's too much to go around, the central atom is going to have to suck it up and deal with it. The central atom is choosing to be the central atom, and its job is to make all the other atoms happy. So then finally, if the octet rule is not satisfied for the central atom, you might have to form a double or a triple bonds, but you do this only if necessary. Whatever you do, don't just look at something and say, hey, I think it looks good if it has a double bond, because you'll probably be wrong. So now we're just going to go through some examples. So give the Lewis structure for dihydrogen selenide. Notice that here's oxygen and here's selenium. It's in the same group as oxygen, so you would predict to have the same bonding pattern as does water. So anyway, I would predict the selenium would be the central atom because it can form 2 bonds. It's also the least abundant. Hydrogen forms only 1 bond and can therefore never be a central atom. So I'm pretty sure this is the way it's going to work. Now I have to prove it. prove it, I have to add up all the valence electrons. So for hydrogen, I have 2 of them. Each one is in group 1. That gives me 2 valence electrons, 2 dots coming from hydrogen. For selenium, there's only 1. It's in group 6. So 6 valence electrons coming from selenium. I add them all up, I get 8. So now, how am I going to distribute those 8 electrons? First into the bonds, right? That takes care of 4. Then to the outer atoms. But the outer atoms, in this case, are already happy. There's 2 electrons in that covalent bond, right? So the hydrogen, as far as it's concerned, has 2 electrons around it, pretending to be 1s2. So now that the outer atoms are happy, I look at the central atom. It's not happy. It only has 4. It wants 8. So I put the 2 other pairs on the selenium atom. And now I look at selenium. It's got 2, 4, 6, 8 electrons around it, which represents S2P6. So because every atom in this molecule is happy, I predict that this structure does exist. We need to do a couple more before you guys start to get the hang of this. What about for sulfur dichloride? So I would predict that sulfur will be the central atom. Okay, it can form up to 2 bonds because it's in group 6. Chlorine only wants to form 1 bond because it's in group 7. So this is what I would predict. Now I have to prove it by adding up all the valence electrons. By the way, notice that in every case, I took the time to add up all the valence electrons in a way that I can check my work and everything, because I don't want to make mistakes. And when I watch students make mistakes, why is it they're making mistakes? Because they didn't add up their valence electrons carefully. So I got 20 dots to go in here. First into the bonds. Okay, that takes care of 4. Then to the outer atoms. So I'll put 2, 4, 6 there. So now chlorine has 8. 2, 4, 6 more over there. So this chlorine has 8. So at this point, I made the outer atoms happy. I still have 4 more valence electrons that go somewhere. They're going to go on the central atom. So then I look for happiness. Chlorine has 8 dots around it, representing S2P6, right? Both of them. What about sulfur? Sulfur also has 8 valence electrons around it. So I predict, because every single atom in here is happy, that that would be possible. What about nitrogen trichloride? So I would predict that nitrogen would be the central atom, right? So I would predict this would be true. Now to prove it, I got to count up all the valence electrons. I get 26. So first into the bonds, that takes care of 6 of them. Then I would put them into the outer atoms. So another 6, another 6, another 6. And I got 2 left over. Where is it going to go? On the central atom. Then I check for happiness. Oh, everything has 8 dots around it, right? Everything's happy. I predict that that's possible. What about carbon tetrachloride? I would predict that carbon would be the central atom. Okay. With 4 chlorides around it in a symmetrical way. So this is what I would predict. So then I count up all my valence electrons. I got 32. So 2 in each bond. So 2, 4, 6, 8. So then I got to put the outer atoms happy. So 6 more, 6 more, 6 more, 6 more. And guess what? I used up all of my valence electrons. Let's see if it makes everything happy. 8, 8, 8, and 8. And the central atom has 8. So I would predict that that would happen. So what about for formaldehyde? Now, formaldehyde is a common name. I didn't give the systematic name here, but you could say dihydrogen carbon oxide. That's fine. But normally would name this with the organic chemistry nomenclature. But anyway, formaldehyde is fine. So I would predict that carbon is going to be the central atom. I know it's not going to be hydrogen, because hydrogen can only form one bond. It can never be a central atom. And carbon and oxygen are both there in the same amount. But carbon can form 4 bonds. Oxygen, only 2. Does that make sense? And I'm getting that from looking at the periodic table. So here's carbon, which I can't see where my finger is. There's carbon. To get like a noble gas, it's going to have to share 1, 2, 3, 4 electrons. In other words, form 4 bonds. Oxygen only needs 2. So this is what I would predict, that bonding arrangement. So notice, if you follow my procedure, which by the way is so good and different than most of the stuff on the internet and in textbooks, should be patentable. I should be rich. But because you followed my procedure, you won't get confused by putting a hydrogen on the oxygen right there. You would come up with this. So anyway, now we have to prove that this is possible. So I count up all my valence electrons. Please do it carefully. 12. So where am I going to distribute them? First into the bonds. That takes care of 6. Then hydrogen doesn't need any more. So the rest of the 6 are going to go on the oxygen. And now I look for happiness. Oxygen has 8. It's happy. Hydrogen has 2. It's happy. This hydrogen has 2. It's happy. This carbon has 6. Is carbon happy?
No.
The answer is no. So what will we do to try to make carbon happy? Now say you're hydrogen. You have 1 electron of your own, 1 electron that you're sharing with the carbon, but you don't have any excess to give up. But look at oxygen. It has 6 of its own, is borrowing 2 more from the carbon. So now the psychology would be, you're oxygen. You have enough electrons for yourself, and your really, really close friend doesn't. So what would you do?
You share.
And by the way, for years now, I started off with this. I walk into the classroom with my Hello Kitty bag, and the students are kind of giving me a weird look and everything, and they're thinking, oh, that must be your granddaughter's Hello Kitty bag. And then I would say, well, I don't have a granddaughter. That's mine. And then I got too much models, so I end up with this Hello Kitty bag. So I walk in there and I got a Hello Kitty bag inside the Hello Kitty bag, and then they think, oh, that must be your granddaughter's Hello Kitty bag. And I have to say, no, hers is smaller than mine, and she can't have mine. But the whole point was this. It was originally an experiment. So I gathered up all these models, which basically I bought myself. My wife bought some. And then everybody that teaches chemistry wants to borrow them. So now when I need them, they're not there. So I put them in the Hello Kitty bag. And you know what? Not a single professor has ever borrowed my Hello Kitty bag. Not even the female ones.
You just outsmarted them.
I don't know why. You have to embrace Hello Kitty. It's a way of life. So here's the other thing about it. So this guy has enough, this guy doesn't. Some people might be thinking, oh, well, supply and demand, you raise the price. And others would say, well, what would Hello Kitty do? They would share. Because everything in the Hello Kitty world is about happiness. So is chemistry. It's all about happiness. So I'm taking this non-binding electron pair that I put in red, and I'm turning it into a double bond. Now let's see what happens. How many electrons are around that oxygen? 2, 4, 6, 8. Sharing doesn't make you lose any valence electrons around you. And what about the carbon? 2, 4, 6, 8. Now the carbon is happy. So I predict that this bonding arrangement is possible. We made every atom in there happy. What I should be doing is showing you structures of these as we move forward, just to give you a little bit of an idea. So I'm going to do that. I know it takes a minute. So here's a three-dimensional model representation of that formaldehyde. So here's the carbon, here's the oxygen. So I got 2, 4, 6, 8 electrons around the oxygen, 2, 4, 6, 8 electrons around the carbon. Now look at the shape right here. I'm giving you a preview of what we'll do next. I got 1, 2, 3 regions where I see electrons. These 3 regions are going to repel one another. And when I do that, I can see that the shape of this molecule is this. You see that? This shape is flat, so we use the word planar, and trigonal. This is flat and trigonal. Does that make sense? Because that's the way that keeps the electron pairs as far apart from one another as possible. So this is something else to think about. So then here's another example. What about oxygen? Okay, that's the only possibility I can come up with. So then what do? We have to prove it. So there's 2 in group 6, so that's a total of 12 valence electrons. First, I'm going to put them into the bond, then putting them into each of the atoms. So here's 2, 4, 6, 8, 10, 12. Okay, that's what I can do. So then I have to look for happiness. Okay, this has 8, so that's happy. This has 6, so that's not happy. So what would you do to fix that? Share some valence electrons. Make a multiple bond. In this case, the double bond satisfies it. 2, 4, 6, 8, 2, 4, 6, 8. Okay, so questions so far?
I've got a question on the setup for the valence electrons. So if we can go, I mean, maybe we can go back to sulfur dichloride, for example. Sulfur, as I understand it, it has 6 pairs and there's only 1 sulfur atom. And that's why you arrange it that way, correct?
Well, sulfur is in group 6, so it has 6 valence electrons, right?
6 valence electrons, okay.
You right there?
Let me see here. Yeah, okay, 2, 4. Well, I guess this is where I'm a little confused is because, I mean, those two pairs that are sharing with chlorine, doesn't that mean that there are 8 electrons for sulfur?
As the element in group 6, it starts out with 6.
Okay.
But to become electronically stable, it wants to have 8. So by sharing an electron with that chlorine, an electron with that chlorine, now it has 8.
And then with chlorine, there's 2 chlorine atoms, and chlorine starts with 7,
Right,
and then it has an additional one because it shares with sulfur.
exactly. So
I
now
see.
it has 8 around it.
Okay. Okay, thank you very much.
And if you're a chlorine atom, that's your goal in life.
To be happy.
Yep.
Yeah.
Essentially, like every atom, as long as they're not a noble gas, is trying to become like a noble gas.
Yes,
And so when they come together, they're able to share electrons to all become like a noble gas. Like the whole element is trying to become stable.
right, right. So essentially, if you take any of these apart and have them as individual atoms, they're not as stable as when they go together and form something more electronically stable. So forming molecules is a way to get more stable.
And just to confirm, it's how many valence electrons, right?
Yeah, because valence electrons are the ones that are either lost, shared, or gained, right? In
Okay.
a chemical
Yeah.
reaction.
Right. Okay.
What do we do with ionic compounds? So you take electrons from the metal cations according to the positive charge, and representative metals should have no dots around them. Transition metals might have some remaining dots. Then the bracket between a metal and a non-metal represents the ionic bond. So this is how we represent the ionic bond right here. So put brackets around a monoatomic anion, put the charge at the upper right. Then you do the same thing. You add up all the valence electrons using the group number from the periodic table, and then you add electrons according to the negative charge. So for a monoatomic ion, you should get 8 dots around that nonmetal, like we have here. So for polyatomic ions, we do 1 and we do 2A, and then we have to follow the sequence for using that we came up with for covalent compounds. But we'll do that in examples. So this is what you're given. Metal, non-metal, there's going to be an ionic bond between them. So my style of doing this and teaching this is that you follow the same pattern. You don't take one chlorine here and put it over here and try to do all that stuff. You got 2 chlorine ions here. That means you got 2 chlorine ions there. Okay. So what about for magnesium? Magnesium loses its 2 valence electrons and gets a +2 charge. Chlorine gains an electron to get a -1 charge. So you can see that we've already compensated for the charge, right? This is a neutral molecule. So how do we count up the electrons that go on to the anion? Well, chlorine, there's 1 of it in group 7, so it came with 7 of its own. That -1 means it got 1 from somewhere else. Most likely it's going to be the magnesium. So that gives us a total of 8 dots to go on the chloride ion, 2, 4, 6, 8. So magnesium is happy because it's now S2P6. Chlorine is happy because it's now S2P6. You follow that?
So the non-metal gains electrons from the metal, and that's how they become stable.
Exactly.
And then basically, there's no lines like covalent bonds, but
Right.
So what exactly like shows that they're bonded together? Because since it's not like a covalent bond, you don't see like a line.
That's positive and that's negative. It's an electrostatic attraction. That is the ionic bond.
Okay. Yeah, right. Like if you were to like take a model, it would still have a bond, right? Or no?
No, you wouldn't.
Oh, so they're just since they're differently charged, they just attract to each other, and that's their bond.
Yeah, exactly. Right. So as we'll talk about later, if I take an entity and it's not neutral anymore, like the other molecules we looked at, it's either positive or negative. That means it has either lost electrons or gained electrons, and it becomes fully charged. So a positive charge will be fully charged and attracted to that negative charge. And that's the definition of an ionic bond. So let's just do another one. Here's sodium sulfide. So again, I just follow the same way of doing it. So what does sodium do? It likes to lose one electron to become like a noble gas. Sulfur likes to gain two to become like a noble gas. So for sulfur, I got one in group 6. I start off with 6 valence electrons. I'm getting 2 more because of that -2 charge right there for a total of 8. Here's another one, aluminum nitride. Okay, so there's the Lewis dot structure for the aluminum ion. Here's the Lewis dot structure for the nitride ion. I mean, we're going through this procedure, but because these are mono ions, we're doing the same thing that we did at the end of chapter 9. So let's see, here is aluminum sulfide, similar type of thing. And then we get to something that needs some explanation. What happens if you have a polyatomic ion? How do I tell it's a polyatomic ion? Well, here's a metal, and then, oh, it doesn't have one nonmetal, it's got 2 nonmetals. And what about the bond between a nonmetal and a nonmetal? What did we say those were called? Covalent bonds. So these are bonded together by covalent bonds, but this is bonded to the sodium by an ionic bond. So here's the ionic bond between the sodiums and the carbonate. And then I'm looking at this right here. Which one is going to be the central atom? Carbon or oxygen? Well, carbon can form 4 bonds, whereas oxygen can only form 2. Plus, there's way more oxygens. So I would say that carbon would be the central atom. Then I put the outer atoms around it in a symmetrical way. I can't do symmetrical with, with a word processor, but that's close enough to it. So then the Lewis dot structure for the sodium ion is simply that. But now I have to follow the rules for covalent compounds in here. So I got carbon. That gives me 4 valence electrons. 3 oxygens give me 18, and that -2 gives me 2 more, so for a total of 24 valence electrons that go in here. Okay. So where am I going to put them first? Into the bonds, right? And then to the outer atoms. So here's 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I used up all my valence electrons. And then what is the next step? We look for happiness. And you can think Hello Kitty. So 8, 8, 8. Uh-oh, only 6. So right now, carbon is not happy. So how do we make carbon happy? We share. So notice that I could share from here, like what I did, but I also could have shared from here, or I could have shared from here. In another chapter, we'll be talking about that. Those are what's called resonance structures. Okay, so just keep that in mind. I can draw 3 resonance structures for carbonate because I can put that double bond in one of 3 different places without moving these atoms anywhere, just moving the electrons.
I have a question, Professor.
Yeah.
I thought covalent bonds were only occurred with metal to metal.
You mean non-metal to non-metal?
Oh, that's it.
Yeah, that's what we're doing right here.
Gotcha. How about metal to metal? Would that be ionic?
No, that would be the metallic bond, which we don't normally draw like this.
Okay.
Yeah. Okay, well, anyway, that's a big step right there, and I gave some really good examples. Then the next thing is trying to figure out what is the shape. So this has a very scary name, valence shell electron pair repulsion theory, or VESPER, they call it. And I remember being an undergraduate trying to learn this stuff, and I just remember this words just made it seem more complicated than it really is. What does that mean, valence shell? We're just talking about valence electrons here, and they repel each other. And yeah, it's a theory. So we do this without even having to know this name. It's just like, why do we even use this name? So what we do is we count up the number of number of electron pairs around the central atom, both bonding and non-bonding. And we'll simply call them reds, which means regions of electron density. So a double bond or a triple bond counts as only one region of electron density. Other textbooks might use the term steric number, and I think it just takes away from what we're really looking at. We're holding a model in our hand or on a piece of paper, and we're looking at electrons. Why the term steric number? I don't know. If there are no bonds, it is either an atom or a monatomic ion. And many molecules do not have a central atom, and we just call them diatomic. So for example, look at hydrogen chloride. Okay, so here's 8 electrons around chlorine. Chlorine is happy, S2P6, 2 around hydrogen. Hydrogen is happy, it's 1s2. There is no central atom. So there is no regions of electron density around the central atom because there is no central atom. The shape, therefore, is simply diatomic. Same thing for oxygen. What are the bond angles? There is none because there's no central atom. So let's just go through this. If there are no regions of electron density, like in oxygen, the shape is simply diatomic. Here's the possible shape, the bond angles, there are none. What if it's linear? Here's an example of a linear molecule. This is a carbon atom. I got 1, 2 regions of electron density. Negative charge, negative charge. How do I get that negative charge as far apart from one another? You put them on exact opposite sides. So therefore the bond angle is 180 degrees across here. What about across here? Same thing, right? So this has 2 central atoms, but both of them are linear. So the whole molecule is linear. And the bond angles for each is 180 degrees. What about if you have 3 regions of electron density? Then it's called planar trigonal, trigonal planar, whatever you want to call it. The bond angles are 120 degrees. So, oh, here it is. So right now, this is simply an atom. There is no bond angles. Now it's diatomic. Now it's bent. Now it's trigonal and it's planar. You see that? And what about the bond angles? In a circle, there's 360 degrees in a circle. If you take a circle and divide it up into 1, 2, 3 pieces, the bond angles now become 120 degrees. What if you have 4 regions of electron density? Then you have this shape, right? So this shape is known as tetrahedral because there's 4 sides. It's like a tetrahedron, right? So here's one side on my hand, 2, 3, and then 4 sides. And so for this geometric shape, the bond angle, if you look at that bond angle there, it's greater than 90, isn't it? 90 would be something like this. It turns out to be 109 degrees. And it's like if you take your fingers and go like this, and then your other hand and go like that and put them together, then your fingers are basically forming a tetrahedral. And that's about 109.5 degrees. Okay. So notice that the shape here, that's 109.5 degrees. What if I take off an atom? The shape is different, but the bond angles are still 120 degrees. I mean, 109.5 degrees, right? Bond angles don't change. What about this? Still 109.5 degrees. The bond angle in water, which this could represent 109.5 degrees as an approximation. So for Chemistry 100, those are the only ones that you need to know. For the biochemistry students, and I am doing this at the same time because it does help the Chemistry 100 students understand more. What if you have 5 regions of electron density, and you get this shape right here, which is pretty much the most complicated one. So here's this shape right here. Notice that I have 2 that are axial, and then I have 3 that are equatorial. See that? And so we can just simply know these bond angles. That right there looks like 90 degrees. Between here and here is 180 degrees. And what about that? That's the same as this was. It's 120 degrees. So when you have 5 reds, it is the most complicated because you have 3 different bond angles there. When you go to 6 reds, then it's not quite so complicated. You can see that there's 90 degrees here and 180 degrees there, and that's all there is. Okay. So let's go look at some of the names of these 2. And these are called what's called expanded octets, and they violate the octet rule. Because look, there's the central atom, 2, 4, 6, 8, 10 electrons around the central atom. That violates the octet rule. These are exceptions to the rules. Same thing over here. there's 12 electrons around that central atom. Okay. So let's analyze the names a little bit. Hexahedral. What does that mean? Hexa means 6. So there's 6 sides to this. So here's 1, 2, 3. And then on the top I have 4, 5, and 6. So it gives you a 6-sided shape. Another name for it is trigonal. And then here's one pyramid, and then here's the other pyramid. It's bipyramidal. Okay. And for the octahedral, there's 8 sides. So on the bottom, 1, 2, 3, 4. And on the top, 1, 2, 3, 4. Octahedral. But another name for it is that it's square, and here's a pyramid, and here's another pyramid. So it's also bipyramidal. Okay. So again, for Chemistry 100, you have to deal with only up to 4 reds. Okay. So now the molecular shape is revealed when you ignore the non-binding electron pairs and only look at the atoms. So again, let's go back to water. Okay. So here's the water molecule. When I look at the water molecule in X-ray diffraction, I see the nuclei. I don't see these electron pairs right there. So this is what it sees. Okay. So the shape, therefore, is bent. Okay. Okay, hold on a second here. Let me try to find figure 1. See how this pops up. Come on, open. Okay, so this is what I want you to look at. So here they're calling it number of electron dense areas. We just called these reds, right? So if you got 2 reds, it's linear. If you got 3 reds, it's planar trigonal. So that would be like this, right? But what if you take off one of the atoms? What do you have? It's bent. Because the X-ray diffraction does not see this. This is what X-ray diffraction sees. It's bent. The bond angles are still 120 degrees because that unvisualized electron pair still pushes the other electron pairs down. Okay. So what about the tetrahedron? So here's the tetrahedron. What if I take off one of the atoms over here? Now, what do we call this? This is called trigonal pyramidal, or I just say pyramidal. Okay? What the X-ray diffraction would see is this, right? But that doesn't make any sense. Why would these 3 hydrogen atoms be pushed down like that unless there was an electron cloud up here, oops, pushing them down? But nevertheless, I would simply call this pyramidal. If I take off one more, then it's like water, it's bent. I can go further than this one does. If I take off another one, What is this shape? It's simply diatomic. There is no central atom. Okay.
Wait, can you show how that's diatomic? So that just means there's two elements, right? Or two
Yeah,
atoms.
there's no central atom.
Right.
If there's no central atom, then it's just diatomic.
Okay.
Yeah. Okay, then again for the biochemistry students. So here's 5 reds. So it's called trigonal biopyramidal or hexahedral, right? And I notice that I have 2 different kinds of atoms. I have these the axial ones, and I have these equatorial ones. So as it turns out, these 2 right here have the least amount of repulsion there is from each other. So if I take one off, it's not going to be one of these that are axial. It's going to be one of these that are equatorial. These equatorial ones are being repelled because there's 9 degrees here, 9 degrees there, 120 here, and 120 here. But these are like 180 from each other. So I'm going to take one of these off. And the shape is now called, in this case, seahorse. Sometimes it's called seesaw. Because, I don't know if you can see this or not. Look, I think somebody before me actually had a sense of humor, and they were chemistry teachers. If I take one more off, then it's now called T-shaped. So you can see the T right there, right?
How would you determine what to take off? You would take off the one with the least repulsion?
Yeah, which turns out to be all the equatorial ones, all 3 equatorial ones.
But how do you know which is equatorial? I mean, like, because if you rotate the atom, then it would be.
Yeah, but you see, keep your eye on the axial ones. These are as far apart from one another as possible. If you look at 2 equatorial ones, no, they're closer together.
Oh, I see.
Yeah.
And so wait, so you take away the ones that are equatorial because they're weaker?
No, because there's more repulsion between them and the other electron pairs.
So if they were to basically escape, you would want to take off the biggest one first, or the most force first, because it'll relax the rest of the atom.
Well, in this class, we're not going to be doing things like this one is big and this one is small. They're all going to be the same. Yeah. When you get to organic chemistry, we do some stuff like that, but yeah, not very often.
Okay.
So anyway, you get what I call Mr. T. And so if I take off one more, then it's linear. If I take off one more, then it's simply diatomic. Okay. So let's see, put that back together. Then finally we get to the octahedral. And these are all identical. It doesn't matter which one I take off. So if I take one off, notice that what it says, it's square pyramidal. This was bipyramidal. I take one off, now it's not pyramidal, it's bipyramidal, it's just simply pyramidal. Now, this particular atom here is being repelled at 90 degrees from 1, 2, 3, 4 atoms. So these right here are only 90 degrees from 2 atoms. So again, the next one I'm going to take off is going to be that one. So you go from bipyramidal to pyramidal to no pyramidal, which is now basically planar and square. See that? Square planar. If I take one off again, it doesn't matter which one, they're all the same. I get Mr. T. Mr. T keeps coming back, right? First he was the scary guy in the TV show, then he became a cartoon character, then they, I don't know what they did, made a movie or something, but Mr. T's acting career was, I pitied the fool that, and then you could put in a couple more words. So if I take one more off, I'm going to get linear. If I take one more off, it simply becomes diatomic. Okay. So here's their idea of trying to show you bond angles. Somehow I get the feeling that they just want you to memorize this stuff. I think it should be almost apparent. So here's what I did. It was the same thing, but I didn't have pictures or anything, so I used that figure. Okay. Well, what if you have a molecule with more than one central atom? So look at this molecule right here. Okay. Let's figure out how we got that. So here's the formula. It doesn't tell you what atom is bonded to what atom. So you have to recognize that there are two central atoms and they're nitrogen. Then the oxygens are going to be outer atoms. So it's just another thing you have to remember. But if I make nitrogen two central atoms, I put the oxygens around it in a symmetrical way. So that's what I would predict. And then I counted up all the valence electrons. And then I put them in the bonds first, and then to the outer atoms. And the last step is you check for happiness. So happy, 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 happy. Oh, the nitrogens are still sad. So what do we have to do? We have to share. So I can make this nitrogen happy by sharing from that oxygen or from that oxygen. Again, that would give us resonance structures. Here I just did it with this one. But look at this other one. I can't share from the other nitrogen because nitrogen is deficient. But I can share from this one or from that one, which gives me more resonance structures. So this right here gives me every atom happy. See if I have a model made. I don't, but I can make one pretty quick. So I didn't put all the non-binding electron pairs on the oxygen. So here's the two nitrogens. Here's two oxygens bonded to that nitrogen and two more bonded to that nitrogen. Notice that for a double bond, you really cannot rotate them around. But for this single bond, you can rotate them around like this. Can you see that? But the point we want to make right here, if I look at this central nitrogen right here, I have 1, 2, 3 regions of electron density. All of them have atoms on it, so the shape should be planar and trigonal. You see that? That's the shape right there. Bond angle is 120 degrees. Same thing over here. No matter what I do, it's still going to be planar trigonal. So here's a molecule that is quite complicated. Oh, somewhere, here it is. And in a Chemistry 100 class, I can't think of anybody who would show you this besides me. But I think you can understand this. I think it's very pertinent. For the biochemistry students, if you take second semester biochem, which is 341 at Manoa, then you'll be doing this stuff. You'll be studying carboxylic acids and alkynes and doing all kinds of stuff like that. But for right now, here is the molecular formula. There is no way I expect you to see this and come up with this or this. If I give you the partial structure, that would help a little bit. But right now, I know you can't do that. But here's the point. Once you knew how to figure this out, then you have to prove it. So you count up all the valence electrons. First into the bonds, right? All those bonds. And then into the outer atoms. Then you try to make every atom happy. And what you'll find is that you will be forced to put a double bond between that carbon and that oxygen. And you'll be forced to have a triple bond between those two carbons. There's no other way to meet the octet rule and the duet rule for every atom in there. Anyway, here's my point for doing this. Look at carbon number 4. That's a central atom, isn't it? Hydrogen is not a central atom. That carbon is a central atom. How many regions of electron density? 2. What should be the shape? Linear. What should be the bond angles? 180 degrees, right? What about carbon number 3? Same thing. 2 regions of electron density, 180 degrees. What about carbon number 2? I got 1, 2, 3, 4 regions of electron density. That makes it tetrahedral. What about carbon number 1? I got 1, 2, 3 regions of electron density. That makes it planar trigonal. What about the oxygen? Got 1, 2, 3, 4 regions of electron density. So I would start off like this. 2 of them don't have atoms on it. So I would get this, and the shape of this is what?
Bent.
Exactly. So now you can see that all these different things that you learned on very simple molecules can also be applied to very complex molecules. So I know this is a lot. Well, like most chapters in chemistry, that's a lot, isn't it? But
Yeah.
I think we're getting the gist of it, we're getting the context of it, and then we can come back and go through examples and solidify a lot of these concepts. So what about the difference in electronegativity? This is C, right? We went all the way from A through D in the beginning with water. So the electronegativity is the ability of an atom to pull electrons towards itself in a bond. It's a calculated number. So, but that doesn't necessarily help us. We wanted to get a little bit more quantitative. So what we do is we take the absolute value of the difference between the two atoms. We call that the difference in electronegativity. So for example, for hydrogen chloride, hydrogen is 2.2, chlorine is 3.16, And you guys should find this on side 2 of your periodic table. So here's side 2. What number is it on this one?
What exactly are we looking on side 2?
Side 2 of the periodic table. That number right there is the electronegativity. And you can look at the
table.
table thing down here. Yeah, tell you. That's where I got those numbers from. So what we're interested in is the relativity. What is the relative electronegativity from one to the other? And this happens to be 0.96. So this is how you get the difference in electronegativity. And double and triple bonds are treated the same as single bonds. And then I made this table or cutoff or whatever, showing you the cutoff. And this is what we'll use for this course. So if the difference in electronegativity is less than 0.5, then we'll consider it to be a nonpolar covalent bond, meaning that there's no significant dipole. The electrons are shared fairly equally, so we don't do anything. We don't put partial charges, right? And so what does this mean? What does it mean if the difference electronegativity is 0? So for chlorine gas, for example, 3.16 minus 3.16, difference is going to be 0. What does that mean? That means that the electrons are shared perfectly evenly between those two atoms. Okay, well, what if the difference in electronegativity is between 0.5 and 1.7? Well, then we call it a polar covalent bond, and this is what we saw in water, polar covalent bonds. There is a significant dipole because the electrons are not shared equally, and we use partial charges. The atom with the largest electronegativity gets the partial negative. So chlorine is 3.16, this is 2.20, so electrons are being pulled in that direction. Here's what I mean by I'm trying to show that right here. They're not shared equally like they are here because chlorine has a much stronger electronegativity than hydrogen. So you create this dipole right here. This molecule right here behaves like a magnet. This likes to be dissolved in water. This likes to be a gas. Does not behave like a magnet. This one does behave like a little magnet. What if the difference in electronegativity is greater than 1.7? Now we have a very large dipole. What we do is we pretend that the electron is actually transferred from one to the other, from the metal to the non-metal. So we use full charges. So a couple of things I want to point out here. Notice that we can have absolute white with no gray. That's when difference electronegativity is 0. And we just have a continuum going from a little bit gray to a little bit grayer to finally like kind of a dark gray, and it never gets black. So we don't have a cutoff right here and a cutoff right here. It's simply a slow progression. But somewhere along the line, somebody has to decide, well, what are the cutoff values to put it in one of these three categories? And this is what I was really disappointed with looking at textbooks and stuff like that. They simply go through all this stuff and many times don't even give you a cutoff number, which is ridiculous. Students really need to have something to go by. You can't have everything in the world be a nuance, if you know what I mean. So very few, if any, textbooks are going to go through this. Look at the very top of side 2. Hopefully you can see that. It says percent ionic character of a single covalent bond. So what you do is you take the difference in electronegativity, you go across the top, and you simply read down. So 0.5 electronegativity difference corresponds to 6% ionic character. If it's 6% ionic character, what is the other 94%? Covalent character. So over here, why did I choose 1.7? If you find 1.7 on there and read straight down, you get 51%. So for me, trying to find a common sense way of explaining this to people, I'm just going to say, well, you know what? If it's greater than 50% ionic character, let's call it an ionic bond. Does it necessarily behave 100% like an ionic bond? The answer is no. And we'll talk about that a little bit later. So that's the reason why I put the percent ionic character in there, but these are the cutoff values. So if it's less than 0.5, you don't do anything. If it's greater than 1.7, you add full charges. Anything else? Partial charges. Those are polar covalent bonds, which could lead to having that molecule behaving like a little magnet. Okay. So is there a difference between 0.50 and 0.49? Not really. Okay. So what do we do here? How does this help us? So here we have formaldehyde, which we already did the Lewis-Dot structure. How do I know how to treat the bonds? So here's the difference in electronegativity between carbon and oxygen, this bond right here. It's 0.89, which falls into this category. So I do have to put partial charges on it. So the oxygen is the most electronegative, it gets the partial negative. That carbon therefore gets the partial positive. What about between carbon and hydrogen? That's only 0.35. Oh, that's in this category, nonpolar. What do I do? Nothing. So now, how does this help us understand the behavior of formaldehyde? This molecule has a dipole in it. This molecule behaves like a magnet. This molecule is going to be attracted to a water molecule because a water molecule is also a magnet. So does this answer the question? Does formaldehyde dissolve in water? The answer is yes, because they both behave like little magnets. Would this molecule align itself in an electrical field such as presented by a chloride ion? The answer is yes. If I had a chloride ion right here, it's going to attract this side and repel that side. So it's going to line up according to the magnetic field of that chloride ion. And what about oxygen? Why is oxygen gas a gas? The bond has a difference electronegativity of 0. There is no dipole in there. There is nothing in the oxygen molecule to make it act like a little magnet. That's why you find it as a gas. It's not attracted to things. So anyway, just to reiterate, the difference in electronegativity is used to describe the behavior of a bond. It is not used in naming. It's not used in drawing Lewis structure, right? And our convention was, if we see a metal and a non-metal we do not draw a covalent bond. We draw it as an ionic bond, and we don't look at the difference in electronegativity first to make that decision. We just do it. So I'm a little bit out of time here, but I don't know if I should run through this or not. Or maybe I'll do it next time. So I'm sure you must have a lot of questions right now because this is a lot of material. And there was a reason why I wanted to get through all this material all at once, because you need to get that perspective. And what you should do now is go back to the beginning of this chapter and go through with what we did here with water and reconcile all that stuff that you've learned and apply it to this short little sequence right here. It's not extremely complicated. It's just a lot of stuff to digest. But once you get it digested, it's really not that complicated. I can do it. So anybody have any questions before we have a weekend break?
I have a question, but it's not regarding chapter 10.
It's regarding?
It's regarding the periodic table and the transition metals.
Uh-huh.
I know it's been described throughout the chapter as having, it doesn't follow, yes, it doesn't follow the rules.
Right.
And I just wanted to clarify, what does that mean?
Well, you cannot, like say, for example, I can look at fluorine right here, and I can predict what it wants to do. I can look at lithium right here, and I can predict what it wants to do. But I can't look at, say, iron and predict what it wants to do by just on its position on the periodic table.
When you say predict what it wants to do, you're talking about whether it wants to gain or lose electrons, right?
Exactly. What charge it's going to form, what number of bonds it's going to form, and all that kind of stuff. Because the transition metals, the ones in the middle at least, can never become like a noble gas. It can never become stable.
So they follow, they're all exceptional in the way that they react.
Exactly.
Okay.
I mean, we can look at other details and theories and stuff like that and predict stuff, but it's all different rules.
Okay, thank you.
So exam 2 is going to start on Monday and Tuesday for the biochem students. And then for Chemistry 100, it'd be the week after that.
Wait, can you say that one more time?
Yeah, so biochem, exam 2 is on Monday and Tuesday.
Oh, snap.
So I'm going to go through and post some answer keys to homework right now. And then I'm going to send an announcement about that. Okay.
Okay.
Do we have a review session on Unit 2?
Well, you may notice that we're behind in the biochem. Or not. We're perfectly fine with the Chem 100. So I can do one, but it would have to be on Monday, and then I would have to give another lecture on Monday also. If you like that, I could do one like, say, from 11 to 12 maybe. Do a review.
That would be good.
Yeah, okay. So I will do that. And I will have to remind myself to do that.
And then we'll, so then there'll be like lecture after?
Yeah. Yeah.
Oh, from 12 to 1:30?
Yeah, and that'd be finishing chapter 10 and starting chapter 11.
Yeah.
Yeah.
All right.
Okay, so any other questions?
I had a question. Would there be any way like we could have review from like 10:30 to 11:30, so we have like a little break in between,
Oh, yeah, you could do that.
just so we can like take a breather?
You know, why is it that I'm pushing 70 years old and I don't have to take breaks?
Oh man, I mean you're right. I mean we don't need it, but
Well, I think it's just because, you know, the love of chemistry and the love of teaching, right? Yeah, energizes. Oh, but yeah, we can do that, no problem.
okay.
Okay, so I'll send that out in an announcement. Okay, so any other questions?
Is the exam open notes?
Yep.
So we can use all of like the chapter PDFs that you wrote out.
All of the what now?
Like the textbook chapters, we can look at those during the test.
Yeah,
Thank you.
don't normally do that, but because of the closing of testing centers and stuff, I got no choice. But yeah. Okay, well, you guys have a great weekend. And I'll see you Monday at about 10:30, if not noon.
Sounds good.
Thank you.
Okay, take care now. Bye.